In this lecture, we study countability. Well, here is the outline of this lecture. First, we give some motivation to countability, then definition and example. Okay, so let us give some motivation to countability. Motivation to countability. So in particular, in analysis and in many other areas of mathematics, or other area of mathematics, we deal a lot. We deal a lot with infinite sets. So in analysis and in many other areas of mathematics, we deal a lot with infinite sets. However, we will discover, we will discover that some infinite sets are bigger than other sets are bigger than others. For example, set of real is bigger than set of natural. So among infinite sets, countably infinite sets are small in a definite sense. Countably infinite sets are small in a definite sense. And they are the smallest. They means countably infinite sets are smallest. Smallest infinite sets. So we will define what is countably infinite sets in a moment. And countably infinite sets are convenient to work with. Countably infinite sets are convenient to work with, because one can list its element, because you can list their elements. For example, making it possible to do inductive proofs, making it possible to do possible to do inductive proof. Inductive proof. So, well, we have seen set of all rationals Q. This is dense in R, dense in the set of all reals. Also, we prove that R is uncountable. We prove that R is uncountable, that is not countable, and Q is countable. So we can remark that Q is countable dense subset of R. Thus, Q. So first of all, Q is dense in R, and we will prove that Q is countable. So Q is countable dense subset of R. Q is countable dense subset of R. Therefore, though R is uncountable, still it admits a countable subset, that is Q, countable subset Q, that is close to everything, that is close to everything. So with regard to this course, with regard to this course in particular, the notion of countability comes up very often. The notion of countability comes up very often. So, well, so before going to the definition of countable sets, we recall a few basic definitions. So there is the second item, definitions. So first we recall a few very basic definitions. So definition set A. So let us consider a function. Let f from x to y be a function. Then for a subset A of x, we define f of A. This is equal to the set of all images of the points in A, that is f of A, such that A belongs to A. And this is called the image of the set A under F, called the image of A under the function F. second item, for B subset of Y, we define F inverse of B. This is equal to set of points in the domain X. So X is domain and Y is codomain of the function F. So set of all points X belongs to capital X, the domain of the function F, such that F of X belongs to B, where B is subset of the codomain Y. And this is called the p-image, called the p-image of the set B, or of the subset B of Y under the function F. Under the function F. Third item, the function F is called injective. F is called injective. F is called injective or 1, if f of x1 is not equal to f of x2, for all x1 not equal to x2 belongs to the domain X. Okay. And fourth item, f is called surjective or onto. Surjective or onto if f of x, this is equal to all of y. So f is called surjective or onto if f of x equal to y. So where x is the domain and y is codomain of the function f. And fifth item, f is called bijective. F is called bijective if it is both injective and surjective. If it is both injective and surjective. Okay, so now we remark that, or this is a fact that if a function f from x to y is bijective, then there exists another function. There exists another function g from y to x. So here domain is y and codomain is x, such that f composed with g, this is equal, this is from y to y. This is equal to identity function on y and identity function on x equal to g composed with f from x to x. That is, let us draw a picture. This is x, this is y, this is again x, and this is the function. This is the function f, and this is the function g, and again here we have from x to y function f. And this composition, this is equal to g composed with f, which is equal to identity on x, and this function, this is the composition function f composed with g, and this is equal to identity function on y. So where identity function on y, this is defined by identity y, this is defined by this of y, this is equal to y for all y belongs to y, and identity function on x, this is defined by this of x equal to x for all x belongs to x, where and this function g is unique, and this is called inverse of f. G is called inverse of f, and we denote it by g equal to f inverse, or f inverse equal to g. So this is a notation. And okay, so next we define the following. Next definition: if there exists a bijective map, from x to y. If there exists f from x to y, a bijective map, a bijective function, then we say that the sets x and y, have the same cardinal number. Same cardinal number. Or that x and y are equivalent, or x and y are equivalent. X and y, so let me write y here. X and y are equivalent. And we denote it by x equivalent to y. Denoted by x equivalent to y. So, well, here we have an exercise. Let me use another color for exercise. Show that first item is x equivalent to x for any set x equivalent to x. And second, x equivalent to y if and only if y is equivalent to x. And third one, x equivalent to y and y equivalent to z implies x equivalent to z. And in particular, conclude that this is an equivalence relation. So for first one, identity function will work, and so if x is related to y, then there exists a, for second one, if x is related to y, then there exists a bijection f from x to y, and from this fact, if there exists a bijective function, then there exists g from y to x function satisfying these two conditions. Okay, then so that g is also bijective function. Okay, therefore y is related to x and converse is the same. And just you have to interchange the role of x and y. Now the third one, x is related to y and y is related to z. That means there exists a bijection from x to y and a bijection from y to z. Now you have to compose these two bijection, and composition of bijections are again a bijection that would conclude that x is equivalent to z. Okay, so this is the solution. So write the formal answer of this exercise. Okay. Now we have another set of definitions. So here we define countable sets. So definitions. So let me change the color. definitions set. Previously we have been labeled by definitions. So first one, for in the set of all natural numbers, we defined n sub n, this is equal to set of all one, set of all uh, set of all natural numbers from 1 to n, 1 to, and here we have three dots, read as, and so on up to n. So capital N subscript by small n, this is equal to the set of all natural numbers between 1 and n. Okay, and we go to the next page, item 2. A set X is called a set X is called finite if X is equivalent to n sub n for some natural number small n. So this is finite and its number of elements is equal to small n. Third item, a set X is called infinite, very simple, if it is not finite. If it is not finite, it is infinite if it is not finite. Fourth item, now here is the definition of countable set. A set X is called countable if X is equivalent to the set of all naturals. Okay, item, a set X is called uncountable if it is neither finite nor countable. Neither finite nor countable. So some authors consider finite sets as countable sets. So we have remark here. Remarks. One, countable sets are also known as known as enumerable or denumerable sets. Denumerable. Second remark is some authors consider finite sets as countable sets. Okay, now we have an example. Now we give an example of countable set. So example. So this is the set of all integers denoted by z, which is equal to a set 0 plus minus 1 plus minus 2 and so on. Okay. Now, so this is countable. So basically to justify this, you have to give an example of bijective function f from set of all natural numbers to z. So such a bijective function is defined by f of n. This is equal to n over 2 if n is an even natural number. So if n is even, and 1 minus n over 2 if n is odd. Then one can verify that this function is bijective. This is bijective. And therefore, we say that set of all natural numbers is equivalent to z, that is z is countable. So we have a remark here. So one can see that n is a proper subset of z. So remark, set of all natural numbers, this is a proper subset. So this is subset and not equal to z. So this is proper subset of z, but still there exists a bijective function. There exists a bijective function between them. And therefore they are equivalent. So this is and for finite set, a finite set cannot be equivalent to one of its proper subset. So this comes from pigeonhole principle. Well, so before stop, we have an exercise. This is exercise 2. Show that a set X is infinite, a set X is infinite if and only if and only if X is equivalent to Y, X is equivalent to Y for some proper subset Y of X, for some Y proper subset and not equal to X. Okay, so exercise. Okay, stop now.